Iron is a chemical element with symbol Fe and atomic number 26. It is a metal in the first transition series. It is by mass the most common element on Earth, forming much of Earth's outer and inner core. It is the fourth most common element in the Earth's crust. Its abundance in rocky planets like Earth is due to its abundant production by fusion in high-mass stars, where the production of nickel-56 is the last nuclear fusion reaction that is exothermic. Consequently, radioactive nickel is the last element to be produced before the violent collapse of a supernova, which scatters this precursor radionuclide of stable iron into space. Like the other group 8 elements, ruthenium and osmium, iron exists in a wide range of oxidation states, -2 to +6, although +2 and +3 are the most common. Elemental iron occurs in meteoroids and other low-oxygen environments, but is reactive to oxygen and water. Fresh iron surfaces appear lustrous silvery gray, but oxidize in normal air to give hydrated iron oxides, commonly known as rust. Unlike the metals that form passivating oxide layers, iron oxides occupy more volume than the metal and thus flake off, exposing fresh surfaces for corrosion. Iron metal has been used since ancient times, although copper alloys, which have lower melting temperature, were used even earlier in human history. Pure iron is relatively soft, but is unobtainable by smelting because it is significantly hardened and strengthened by impurities, in particular carbon, from the smelting process. A certain proportion of carbon produces steel, which may be up to 1,000 times harder than pure iron. Crude iron metal is produced in blast furnaces, where ore is reduced by coke to pig iron, which has a high carbon content. Further refinement with oxygen reduces the carbon content to the correct proportion to make steel. Steels and iron alloys formed with other metals are by far the most common industrial metals because they have a great range of desirable properties, and iron-bearing rock is abundant. Iron chemical compounds have many uses. Iron oxide mixed with aluminium powder can be ignited to create a thermite reaction, used in welding and purifying ores. Iron forms binary compounds with the halogens and the chalcogens. Among its organometallic compounds is ferrocene, the first sandwich compound discovered. Iron plays an important role in biology, forming complexes with molecular oxygen in hemoglobin and myoglobin. These two compounds are common oxygen transport proteins in vertebrates. Iron is also the metal at the active site of many important redox enzymes dealing with cellular respiration and oxidation and reduction in plants and animals. A human male of average height has about 4 grams of iron in his body, a female about 3.5 grams. This iron is distributed throughout the body in hemoglobin, tissues, muscles, bone marrow, blood proteins, enzymes, ferritin, hemosiderin, and transport in plasma. Characteristics. Mechanical properties. The mechanical properties of iron and its alloys can be evaluated using a variety of tests, including the Brinell test, Rockwell test, and the Vickers hardness test. The data on iron is so consistent that it is often used to calibrate measurements or to compare tests. However, the mechanical properties of iron are significantly affected by the sample's purity. Pure, single crystals of iron are actually softer than aluminium, and the purest industrially produced iron has a hardness of 20 to 30 Brinell. An increase in the carbon content will cause a significant increase in the hardness and tensile strength of iron. Maximum hardness of 65 Rc is achieved with a 0.6% carbon content, although the alloy has low tensile strength. Because of the softness of iron, it is much easier to work with than its heavier congeners ruthenium and osmium. Because of its significance for planetary cores, the physical properties of iron at high pressures and temperatures have also been studied extensively. The form of iron that is stable under standard conditions can be subjected to pressures up to California 15 gigapascals before transforming into a high-pressure form, as described in the next section. Phase diagram. An allotrope sign represents an example of allotropy in a metal. There are at least 4 allotropic forms of iron, known as alpha, gamma, delta, and epsilon, at very high pressures and temperatures. Some controversial experimental evidence exists for a stable beta phase. As molten iron cools past its freezing point of 1538 degrees Celsius, it crystallizes into its delta allotrope, which has a body-centered cubic crystal structure. As it cools further to 1394 degrees Celsius, it changes to its gamma iron allotrope, a face-centered cubic crystal structure, or austenite. At 912 degrees Celsius and below, the crystal structure again becomes the BCC alpha iron allotrope, or ferrite. Finally, at 770 degrees Celsius, iron's magnetic ordering changes from paramagnetic to ferromagnetic. As the iron passes through the Curie temperature, there is no change in crystalline structure, but there is a change in domain structure, where each domain contains iron atoms with a particular electronic spin. In unmagnetized iron, all the electronic spins of the atoms within one domain have the same axis orientation. However, the electrons of neighboring domains have other orientations, with the result of mutual cancellation and no magnetic field. In magnetized iron, the electronic spins of the domains are aligned and the magnetic effects are reinforced. Although each domain contains billions of atoms, they are very small, about 10 micrometers across. This happens because the 2 unpaired electrons on each iron atom are in the dz2 and dx2-y2 orbitals, which do not point directly at the nearest neighbors in the body-centered cubic lattice and therefore do not participate in metallic bonding. Thus, they can interact magnetically with each other so that the spins align. At pressures above approximately 10 gigapascals and temperatures of a few hundred Kelvin, a alpha iron changes into a hexagonal close-packed structure, which is also known as epsilon iron. The high-temperature gamma phase also changes into epsilon iron, but does so at higher pressure. The beta phase, if it exists, would appear at pressures of at least 50 gigapascals and temperatures of at least 1500 K and have an orthorhombic or double HCP structure. These high-pressure phases of iron are important as end-member models from the solid parts of planetary cores. The inner core of the Earth is generally presumed to be an iron-nickel alloy with epsilon structure. Somewhat confusingly, the term beta iron is sometimes also used to refer to alpha iron above its Curie point, when it changes from being ferromagnetic to paramagnetic, even though its crystal structure has not changed. The melting point of iron is experimentally well defined for pressures less than 50 gigapascals. For greater pressures, studies put the gamma-epsilon liquid triple point at pressures that differ by tens of gigapascals and 1000 K in the melting point. Generally speaking, molecular dynamics computer simulations of iron melting and shock wave experiments suggest higher melting points and a much steeper slope of the melting curve than static experiments carried out in diamond anvil cells. The melting and boiling points of iron, along with its enthalpy of atomization, are lower than those of the earlier 3D elements from scandium to chromium, showing the lessened contribution of the 3D electrons to metallic bonding as they are attracted more and more into the inert core by the nucleus. However, they are higher than the values for the previous element manganese because that element has a half-filled 3D subshell and consequently its d electrons are not easily delocalized. This same trend appears for ruthenium but not osmium. Isotopes. Naturally occurring iron consists of 4 stable isotopes: 5.845% of 54 Fe, 91.754% of 56 Fe, 2.119% of 57 Fe, and 0.282% of 58 Fe. Of these stable isotopes, only 57 Fe has a nuclear spin. The nuclide 54 Fe theoretically can undergo double electron capture to 54 Cr, but the process has never been observed and only a lower limit on the half-life of 3.1 times 1022 years has been established. 60 Fe is an extinct radionuclide of long half-life. It is not found on Earth, but its ultimate decay product is its granddaughter, the stable nuclide 60Ni. Much of the past work on isotopic composition of iron has focused on the nucleosynthesis of 60 Fe through studies of meteorites and ore formation. In the last decade, advances in mass spectrometry have allowed the detection and quantification of naturally occurring variations in the ratios of the stable isotopes of iron. Much of this work is driven by the Earth and planetary science communities, although applications to biological and industrial systems are emerging. In phases of the meteorites Marcona and Chervony cut a correlation between the concentration of 60Ni, the granddaughter of 60 Fe, and the abundance of the stable iron isotopes provided evidence for the existence of 60 Fe at the time of formation of the Solar System. Possibly the energy released by the decay of 60 Fe, along with that released by 26 Al, contributed to the remelting and differentiation of asteroids after the formation 4.6 billion years ago. The abundance of 60Ni present in extraterrestrial material may bring further insight into the origin and early history of the Solar System. The most abundant iron isotope 56 Fe is of particular interest to nuclear scientists because it represents the most common endpoint of nucleosynthesis. Since 56Ni is easily produced from lighter nuclei in the alpha process in nuclear reactions in supernovae, it is the end point of fusion chains inside extremely massive stars, since addition of another alpha particle, resulting in 60 zinc, requires a great deal more energy. This 56Ni, which has a half-life of about 6 days, is created in quantity in these stars, but soon decays by 2 successive positron emissions within supernova decay products in the supernova remnant gas cloud, first to radioactive 56 Co, and then to stable 56 Fe. As such, iron is the most abundant element in the core of reg ions, and is the most abundant metal in iron meteorites and in the dense metal cores of planets such as Earth. It is also very common in the universe, relative to other stable metals of approximately the same atomic weight. Iron is the 6th most abundant element in the universe, and the most common refractory element, although a further tiny energy gain could be extracted by synthesizing 62Ni, which has a marginally higher binding energy than 56 Fe. Conditions in stars are unsuitable for this process. Element production in supernovas and distribution on Earth greatly favor iron over nickel. Hence, elements heavier than iron require a supernova for the formation, involving rapid neutron capture by starting 56 Fe nuclei. In the far future of the universe, assuming that proton decay does not occur, cold fusion occurring via quantum tunneling would cause the light nuclei in ordinary matter to fuse into 56 Fe nuclei. Fission and alpha particle emission would then make heavy nuclei decay into iron, converting all stellar mass objects to cold spheres of pure iron. Occurrence metallic and native iron is rarely found on the surface of the Earth because it tends to oxidize, but its oxides are pervasive and represent the primary ores, while it makes up about 5% of the Earth's crust. Both the Earth's inner and outer core are believed to consist largely largely of an iron-nickel alloy constituting 35% of the mass of the Earth as a whole. Iron is consequently the most abundant element on Earth, but only the fourth most abundant element in the Earth's crust, after oxygen, silicon, and aluminium. Most of the iron in the crust is found combined with oxygen as iron oxide minerals such as hematite and magnetite, as well as in limonite and siderite. Significant amounts also occur in the iron sulfide mineral iron pyrite, but it is difficult to extract iron from it and it is therefore not used. In fact, iron is so common that production generally focuses only on ores with very high quantities of it. During weathering, iron tends to leach from sulfide deposits as the sulfate and from silicate deposits as the bicarbonate. Both of these are oxidized in aqueous solution and precipitate in even mildly elevated pH as iron oxide. Large deposits of iron are found in banded iron formations. These geological formations are a type of rock consisting of repeated thin layers of iron oxides alternating with bands of iron pore shale and chert. The banded iron formations were laid down in the time between 3,700 million years ago and 1,800 million years ago. About 1 in 20 meteorites consist of the unique iron-nickel minerals tannite and carmesite. Although rare, iron meteorites are the main form of natural metallic iron on the Earth's surface. The red color of the surface of Mars is derived from an iron oxide-rich regolith. This has been proven by Mossbauer spectroscopy. The soil of the Moon contains 0.5% metallic iron. According to the International Resource Panel's Metal Stocks in Society report, the global stock of iron in use in society is 2,200 kilograms per capita. Much of this is in more developed countries rather than less developed countries.